Hello students, good morning to all. Hope you all are doing good. Welcome back to the fourth session of quantitative analysis, precipitation titration. The last titration, that is precipitation titrations. So what are precipitation titrations? The titrations involves precipitation are called precipitation titration. Let's understand by its definition. A special type of titrometric procedure involves the formation of precipitates during the course of titration. The titrant react with the analyte forming an insoluble material, and the titration continues till the very last amount of analyte is consumed. The first drop of titrant in excess will react with the indicator, result in the color change and announcing the termination of the titration. See, a special type of titrometric procedure which involves the formation of precipitate during the course of titration. That means while performing titration, we are forming in conical flask. We are forming a precipitate, an insoluble precipitate. Now perform till continue the titration. Last amount of analyte is consumed. The first drop of titrant in excess will react with the indicator. Now we are after complete reaction of analyte, consumption of analyte by titrant. The excess of titrant will react with the indicator, and then sudden change of color will observe. In that is the end point where the color will change. That indicates the completion of the reaction. All the analyte would be consumed, right? So reaction must satisfy these conditions. Precipitation must be practically insoluble. The formed precipitate in conical flask should be insoluble, okay, and the precipitation must be rapid. Precipitation must be rapid and possible to detect equivalent point. There must be color change should be sharp, right, at end point, that is called equivalence point. A method based on the precipitation of insoluble silver known as agentometry. If you are using standard AgNO3 insoluble AgNO3 solution, that particular titration is known as agentometry. And halogens other than AgNO3, so that is non-agentometric titrations, right? Like here halogens can be determined by precipitation as a spanning insoluble mercurous salts HgCl2 and HgI2 are called mercurometry, right? So if you are using AgNO3, that is agentometry. Other than AgNO3, that is non-agentometric titrations, right? Agentometric titrations. Solubility product is the product of concentration of ions in the saturated solution of spangly soluble salts as AgCl constant at given temperature. Now here, how precipitate would be formed. So what is the principle involved in precipitate? See here, solubility product is the product of concentration of ions in the saturated solution of spangly soluble salt. We are taking AgCl in undissociated solid, the first one undissociated solid, and then dissolve undissociated molecule. It can be dissociated to Ag plus and Cl minus, right? Now we are product of Ag plus and Cl minus, right? See, the overall equilibrium is AgCl, Ag plus and Cl minus, where Ag plus and Cl minus represent the ionic concentrations. If you calculate the equilibrium constant, that is product of concentration of products by concentration of reactants, concentration of Ag plus and concentration of Cl minus by concentration of AgCl. Concentration of AgCl is constant in solid, hence denominator will be neglected. Now K equilibrium is equal to K equilibrium to concentration of AgCl is equal to Ag plus and Cl minus that product of equilibrium constant and the product of AgCl, that called solubility product, which was indicated by Ksp, right, is equal to Ag plus, concentration of Ag plus and concentration of Cl minus, solubility constant product, that is, right. Now see here conditions where the precipitation occurs, right? When when the ionic product exceeds the solubility product. So if you are having solubility product and ionic product is the product of ions in the solution, that is ionic product. So when the ionic product exceeds the solubility product, that is ionic product greater than solubility product, the solution is supersaturated and precipitation will occur. There is in that condition only precipitation occurs, that is supersaturated condition. Next, when the ionic product is less than that means ionic product is less than the solubility product, in that case the solution is unsaturated, no precipitation will be occurred, a clear solution will be appeared, right? So in quantitative analysis, excess of precipitating agent is always be employed to ensure the complete precipitation. See here, I'm giving an example here, BaCl2 plus H2S for forming barium sulfate precipitate here, barium sulfate precipitate here. So there are three types of precipitation methods: Morse method, Wallhersa method, Fajans method. So out of these most method, Fajans method comes under direct methods. Wallhersa method is indirect method or back titration method, right? See now first one Morse method. Let's understand Morse method. So Carl Friedrich Moore, scientist, he was introduced this Morse method in 1856. So determination of halide chlorides with silver nitrate using potassium chromate solution as indicators. So it is especially useful for the determination of chloride, right? So see the reaction AgNO3 plus NaCl, which gives AgCl precipitate and NaNO3. So precipitated silver chromate through spangly soluble in water is more soluble than the silver chloride. So and the red color due to the silver chromate does not appear until all the chloride has been precipitated as silver chloride. So how this experiment was performed? So first let us take in conical flask. We are taking NaCl solution, sodium chloride, where you have to estimate the amount of chloride present in that solution, right? Now silver chloride, which was taken in burette. Now adding silver chloride into the conical flask where you are having a sodium chloride along with the indicator, that is potassium chromate solution as indicator, right? Now Ag plus ions comes from the burette. They are reacting with the chloride ions and also chromate ions. So there are two types of compounds are formed, silver chloride and silver chromate. But here the point is silver chromate is having more soluble product than compared to the silver chloride. So first of all chloride ions are reacting with the Ag plus ions and forming AgCl precipitate, that is white precipitate. So while adding Ag plus Ag that is silver nitrate from burette, they are forming AgCl white precipitate initially, right? So after all the chloride ions are reacting, the excess of Ag plus ions are now reacting with the chromate ions present in that conical flask. They are forming Ag CrO4, right? Potassium Ag2CrO4, that is silver chromate. So that is red color. So that means white precipitate could be converted into red. So that's your where red precipitate appears. That's your end point, right? So this method utilizes a chromate as indicator. So chromate forms a precipitate with Ag plus, but this precipitate has greater solubility than that of AgCl. For example, therefore AgCl is formed first. So first I'm telling you, AgCl is formed first, then all chloride ions are consumed. After all chloride ions are Cl minus is consumed, the first drop of Ag plus in excess will react with the chromate indicator, giving reddish precipitate, right? So a red color precipitate is formed. So here is the reaction, that is Ag plus and forming reacting with chromate, forming Ag2CrO4. So first AgCl precipitate is formed. After all Cl minus ions are consumed, the first drop of Ag plus, after here AgCl is completely formed, right? So all chloride ions are reacted. Now the first drop of Ag plus ions in excess will react with the chromate and forming a reddish precipitate. That reddish color precipitate indicates silver chromate, right? Clear? Now here you have to take a precaution, that is in this method neutral medium should be used, since alkaline solution silver will react with the hydroxide ions forming silver hydroxide. So in acidic solutions chromate will be converted to the dichromate. Therefore the pH solution should be kept about 7. So this is always some error in the method. This method, because of a direct chromate solution is used due to the intense color of the indicator. So this will require additional amount of Ag plus for the silver chromate to form, right? So this is the precaution you have to take. So here having some limitations. So allowable pH range is 6.5 to 10. We have to maintain the pH range, that is 6.5 to 10. So below pH 6.5 there is increased the solubility of silver chromate. So you have to maintain above 6.5 and below 10. So because above pH 10 the end point comes to too late. That means for end point it takes much time, right? And silver hydroxide is also precipitated. So that's why your pH should be maintained between 6.5 to 10. So if the solution is alkaline medium, it's acidic with the nitric acid, then neutralize it by adding sodium bicarbonate or borax. So if appreciable amount of ammonium salts are present, the pH should be not exceed 7.2. So in reverse titration, iodides and bromides cannot be titrated. So this is about first method, that is Morse method. So this is direct method, so where you are estimating the amount of chloride ions by using potassium chromate as indicator, and potassium chromate as indicator. Now forming AgCl white press first after formation of after all chloride ions are consumed from NaCl, right? So the excess of Ag plus will react with the chromate ion, that is from potassium chromate. So chromate ion reacting with Ag plus, excess of Ag plus, that first drop of Ag plus after complete AgCl precipitation, this Ag plus reacting with the chromate and forming silver chromate, that is reddish color precipitate. So where we are getting red colors, that's your endpoint. So that is direct method, Morse method, that's precipitation titration. And the second type of method, that is the Wallhersa method. So Jacob Wallhersa, scientist, in 1874 designed the method of estimation of silver ions. So where you are determining silver ions, so in direct acid dissolution by titrating against a standard thiocyanate solution in the presence of ferric salt, ferric ammonium sulfate as indicator. So here you are estimating silver ions in direct acid solution by titrating against a standard thiocyanate. So standard thiocyanate solution, that is thiocyanate solution should be taken in burette. In conical flask you are taking silver nitrate and ferric ammonium sulfate, that is ferric alum as indicator here, right? Now here forming two precipitates again. So from burette, thiocyanate ions, that is SCN minus ions, thiocyanates are reacting with Ag plus ions and as well as ferric ions, ferric thiocyanate and silver thiocyanate will be formed. But first silver thiocyanate is formed, after that ferric thiocyanate will be formed. So see, ammonium or potassium thiocyanate solution is used in conjunction with AgNO3 in the assay of a substance which react with the nitrate, but which cannot be determined by direct titration with the silver nitrate solution. So it cannot determine direct titration, right? So in this method, to halide solution, a known excess of silver nitrate is titrated titrated with ammonia or potassium thiocyanate solution, so which was taken in burette. This is called Wallhersa method. So titrating against the potassium thiocyanate. So in this method, precipitation of silver chloride is filtered off first. If it is necessary, you must filter the excess silver chloride, and that filtrator is titrated with the standard thiocyanate solution using ferric ammonium sulfate as indicator. So you are taking filtered silver chloride and ferric ammonium sulfate in conical flask. Now you are titrating these mixture with potassium thiocyanate from burette. Now titrating with the potassium thiocyanate, the end point a permanent red color is produced due to the formation of ferric thiocyanate, right? So first AgCl precipitate is formed. You have to filter off precipitate. Then that filtrate and adding to this filtrate adding ammonium thiocyanate and adding titrating with ammonium thiocyanate, and also here having a ferric alum, also ferric ammonium sulfate, so that is used as indicator here. So here forming silver thiocyanate and ferric thiocyanate, two compounds are formed, that is silver thiocyanate and ferric thiocyanate. First silver thiocyanate will be formed, after that ferric thiocyanate will be formed. So because the ferric thiocyanate is having more soluble product than silver thiocyanate, so initially first all Ag plus ions are consumed in that beaker, in that conical flask. Ag plus ions are reacting with the thiocyanate ions which comes from burette. The first forms Ag SEN, that is silver thiocyanate, will be formed firstly, and then after all Ag plus ions are consumed, the next drop of thiocyanate will reacting with the Fe3 plus forming ferric thiocyanate, right? So this is an indirect method for the chloride determination, where the excessive amount of standard Ag plus is added to the chloride solution containing Fe3 plus as indicator. So the excess of Ag plus is then titrated with the standard thiocyanate solution until red color is obtained. So where red color is obtained, ferric thiocyanate is formed. So in that case, red color is formed. That means all Ag plus ions are reacted, all Ag plus ions are consumed. After, the next drop of thiocyanate will reacting with the ferric alum, forming ferric thiocyanate, right? So the indicator system is very sensitively used. Good results are obtained. The medium should be acidic to avoid the formation of ferric hydroxide. Here you have to maintain the acidic condition, because to avoid the formation of ferric hydroxide. However, the use of acidic medium together with the added thiocyanate titrate increase the solubility of precipitate, leading to the significant error. So this problem had been overcome by to maintain these procedures, right? So now, so this is about Wallhersa method. So here estimating the amount of Ag plus. So it is indirect method, because we are taking excess silver nitrate and along with ferric alum as indicator, and titrating with potassium thiocyanate. Now this thiocyanate SEN minus ions from burate, which are reacting with Ag plus ions and ferric Fe3 plus ions. So Ag plus ions and Fe3 plus ions are reacting with thiocyanate, but first all Ag plus ions are consumed, all Ag plus ions are reacting with thiocyanate, forming AgSCN, that is silver thiocyanate is formed because of less solubility product. First all Ag1 ions are consumed by forming AgSCN, silver thiocyanate, right? After consumption of all Ag plus ions in conical flask, the next drop of thiocyanate will reacting with the ferric ions, ferric Fe3 plus ions, they forming ferric thiocyanate. Okay, so ferric thiocyanate is reddish color. So where you are the white precipitate will be converted into the red colors. That's your end point. So this is about Wallhersa method. And the next method, Fagen's method. So Fagen's introduce this method. So where you are using a fluorescein and its derivatives are adsorbed to the surface of colloidal AgCl. After all chlorides are used, the first drop of Ag plus will react with the fluorescein, forming the reddish color. So this is the adsorption indicator, right? So among these methods, Wallhersa method is widely used because you can determine detect the end point of the precipitation titration very easily. So here fluorescein and few adsorption indicators are used, fluorescein and dichlorofluorescein. So these two adsorption indicators are widely used. So here consider the titration of Cl minus ions with Ag plus. So before the equivalence point, Cl minus is excess, right? So before performing titration, Cl minus ions are excess, and then adding AgNO solution from burate, this primary layer of is Cl minus, and this represents the indicator in anion. So if you see that AgCl precipitate will be formed. So here initially excess of chloride ions and the formation of AgCl precipitate, while adding Ag plus ions from a burate, silver chloride. So I am forming AgCl precipitate. So by consuming chloride ions, so initially chloride ions are more. So by adding Ag plus ions, AgCl precipitate in the presence of excess of silver ions, right? In the second case, so that's first one before the end point. So beyond the equivalence point, Ag plus is in the excess and surface of the precipitate becomes positively charged. So this will now attract the indicator anion and adsorbed. It is in the second layer. The color of the adsorbed indicator is different from that of an adsorbed indicator. The fluorescent indicator have a -2 charge. In this form, the indicator has yellow-green color. When it is adsorbed onto the colloidal AgCl, it gives the light pink or orange color, right? So if you see that here, you can understand easily these by these two diagrams, right? So if fluorescence will strongly absorb, then and the nitrate ion will reveal its presence on the precipitate not by its own color. So which is the of the solution, Another view of absorption of fluorescent ion is the rearrangement of structure of the ions occurs with the formation of color substances, right? So fluorescent is an important dye with a phthalate group. So this is the structure of fluorescent absorption indicator. So condensing phthalic anhydride with the resonance. So that's the preparation. Sodium salt of fluorescein in water or alcohol. So Fazens and Wolf recommended 1 or 2 drops of indicator for the 10 ml of neutral halide solution, right? So it is rapidly decomposed by light. So it can be used for the chlorides, bromides, iodides and thiocyanate. And the second absorption indicator, dichlorofluorescein, DCF, right? Dichlorofluorescein. So it is a weakly acidic solution condensing the phthalic anhydride and monochloride resonance, right? So 0.1% of solution in 70% of alcohol or 0.1% of solution as indicator. So among these methods, the Wallhersa method is widely used because it can detect the endpoint of precipitation titration very well. Okay. So some limitations of precipitation titrations, a few number of ions such as halide ions, chloride, bromide, iodine can be titrated by precipitation method. Co-precipitation may be occurred, so we have to minimize this co-precipitation. So I would explain co-precipitation, post-precipitation in the next session, that is a gravimetric analysis, where you can understand about this co-precipitation and post-precipitation. Right, so co-precipitation nothing but just precipitation due to impurities. That's co-precipitation. Your first primary precipitate is your precipitate. So along with the precipitate, they are forming precipitate of secondary precipitate, that is because of impurities, that is co-precipitation. That is called co-precipitation. Co-precipitation may occur. We have to avoid this co-precipitation, right? So it is very difficult to detect the endpoint because you are getting precipitates, right? So you're not having solutions, color solutions, you are getting precipitates. So that's why, so it's very difficult to detect the endpoint. So right, this is about precipitation titrations. So the titrations involving precipitation are called precipitation titrations.